Hello again. Only comment to all of you is feel free to call, text or email more. Today I'm going to continue with a historical review. Back in lecture 1 I spoke to you on how we found out, for example, Earth's circumference, the distance to the moon and the distance to the sun. You could see that the ancient Greeks and Romans believed already that the Earth was round and had a fairly good idea about the distance to the moon. That's where the agreement ended. In lecture 2 you have seen why Aristarchus thought the sun was in the middle and how he tried to measure the size of the sun. He failed to convince. Archimedes and Ptolemy perfected the geocentric model where the spherical Earth was in the center of the universe. I will briefly touch on this model next. I will then tell you a bit about what happened in science in the intervening 1500 years. It took us 1500 years until Copernicus' book came around. Copernicus reintroduced Aristarchus' heliocentric model where the sun was in the middle. I will tell you briefly about this dude, but mostly I will be talking about 3 observations: the phases of the moon, the fact that we have seasons on Earth, and the difference between sidereal and solar days. Let us start with the geocentric model. Please click on the link below and watch a 2-minute video that describes the geocentric model, the model of the ancient Greeks where the Earth was in the middle. As you will see, these guys were no dummies. However, the model is fairly intricate and fairly complicated. The link below is to a web page that I've maintained for a few years. In it you'll find a comprehensive table that deals with the history of science between ancient times and the present. Let me summarize in a few sentences. The Greco-Roman world missed some very crucial tools that would have allowed it to accept the heliocentric system if they had those tools. These tools were developed in parallel in India and later on in parts of the Muslim world. For example, the principle of parsimony is something simple that most of you are familiar with, but it wasn't familiar to the ancient Greeks. That's the idea that if there are 2 models that explain a phenomenon, the simplest of these 2 models is more likely to be correct. Guess what the source is of the word revolution, as in the American Revolution, for example? Yes, it is related to Copernicus. Copernicus studied medicine in Italy in the late 1400s. In his spare time he learned Greek books, some ancient Greek books about astronomy, and observed astronomical observations without a telescope, because there weren't any yet. He's done that with his pals back in Italy. Back in Poland he was the king's physician, he was a monk, and he did observations of stars and planets. In 1532, on his deathbed, he published a book. The book is called On the Revolutions of the Heavenly Spheres, hence the word revolutions. A revolution, therefore, is things that revolve around the sun. That's the source of the word. Before we introduce the phases of the moon again, I would like to introduce the great clock called Earth. In the picture below you see the Earth as seen from above. the sunlight is coming from the left-hand side. A person on the side furthest from the sun wouldn't see the sun because Earth is on the way. Since the person is very small and would only see the sun once he goes over the hump just at the very top, that is the place where people see that the time is 6 a.m. A person on the left under the sun experiences the time of 12 p.m. A person that sees the sun disappears on his or her western horizon experiences the hour of 6 a.m., etc. Now, as you're observing the orbit of the moon around the Earth, please take note that this orbit is slightly tilted, hence the new moon does not eclipse the Earth. When you look at a waxing crescent moon in a picture below, what is it that you will see? Since the moon itself is a sphere, you will not see half a moon or part of a circle that's cut with a straight line, but rather you will see a banana-shaped crescent. It's only when you get to the first quarter that you will see half a moon, and then you will see a banana-shaped dark part, which is called waxing gibbous. Waxing, as in you put wax in it, therefore it's bigger and bigger. Full moon is in the opposite side, then it's a waxing gibbous, waning gibbous, third quarter, and waning crescent. Waning as in getting smaller and smaller. You may now go back and forth between the first and second image on this slide and persuade yourself that from your vantage point you will see waxing crescent, half moon, gibbous moon, full moon, waning gibbous, half moon again in the third quarter, and waning crescent. This is another image with the same exact result in mind. Again, you should go through the first and second image and try and persuade yourself that the vantage point is what results in the phases of the moon. Therefore, the phases of the moon are not a result of eclipsing, but rather the result of the juxtaposition of the Earth, Moon, and Sun. Well, it still works if the Earth is in the middle and doesn't move at all. The only caveat is that now the Sun goes around the Earth once in 24 hours, while the Moon goes around the Earth in 24 hours and 50 minutes. Hence it looks as if they make this fake type of period called a month. That's just a result of the fact that the Moon is moving around the Earth a little bit faster. Things get a little bit more complicated as far as geocentric versus heliocentric models are concerned when we are trying to describe the seasons. Notice that for us in the northern hemisphere, this picture is for a person standing at about Kansas City latitude. For us in the northern hemisphere, in the summertime, the sun rises a little north of east, gets to almost above our heads, almost to our zenith point, the point directly above our heads, and sets in the northwest. In fall and spring, the sun rises in east, goes up but not as much, and sets in the west. In the winter time, the sun rises in the southeast, goes up only about 30 degrees above the southern horizon, and then sets in the southwest. The sun's path, the sun's path throughout the sky throughout those seasons is called the ecliptic. The planets are also on that line called the ecliptic. The explanation by Copernicus, Aristarchus, and our modern explanation is that the Earth is spinning on its axis, but the axis itself is tilted. It's tilted a little bit towards the sun in the summer months. It's tilted a little bit away from the sun in the winter months. Interestingly enough, we are not closer to the sun in the summer at all. After all, the northern hemisphere is experiencing summer, and at the exact same time in New Zealand this is winter time, so you can go skiing there. New Zealand is in the southern hemisphere. This, of course, is a little trickier to explain with the geocentric model. Now that path of the sun in the sky and the path of the planets in the sky is easy to understand in the heliocentric model. Both Earth and the planets are orbiting the sun in the same exact plane. What's more, Earth itself is spinning around its axis, and its axis is tilted at 23.5 degrees towards the sun in June. It's tilted at 23.5 degrees away from the sun in December. Actually, that rotational axis of the Earth is pointing throughout towards the very, very, very far polar star Polaris. Hence, we always see Polaris above the North Pole. This is what causes the seasons. So the seasons are the result of Earth's axis of rotation tilt. When we are tilted towards the sun in the northern hemisphere, the sun is closer to above our heads and therefore can warm up the surfaces much more effectively during the summertime. As you will see in the link below, we are also a tad further away from the sun in our own summertime, but that has very little effect. We will talk about the effect that this tiny little difference due to the Earth's elliptical orbit, where we're 1.5% further from the sun in the summer, 1.5% closer to the sun in the winter, we will see this effect in a later lecture. But for now, this is not the reason for the seasons. We are not closer to the sun in the summertime. Try and answer the following question. In our PowerPoints, what I'm trying to do is whenever I have multiple choice questions, I advise that you wait about 20 to 30 seconds. Read the questions, then maybe try and write down something, and afterwards choose if it's A, B, C, and D. When you click on a button, the correct answer will show. In this example, read the question, figure out the answer, and after you do, press on the second loudspeaker symbol to hear an explanation of why that answer is correct. The way to figure this one out, the correct answer of course is summer. The way to figure this one out is to figure out the following. In the summertime, the sun is closest to be above our heads, and we are in the northern hemisphere. As we go around the Earth to the night position, you may see that we in the northern hemisphere are going to be at an angle that will show that the horizon is closest to the same exact line of the orbit of the planets. Since the planets are in the opposite direction of the sun, they will be the lowest in the southern horizon when it is summertime in the northern hemisphere. Whereas in the previous slide you could see the Earth orbiting the Sun and noticing the tilt. Here the tilt is not important at all. In this picture we view the Earth and the Sun from above Earth's North Pole. As Earth goes around the Sun, a person will see the Sun crossing his head exactly in 24 hours, but because the Earth is going around the Sun, he will see a star that's lined up with the Sun a little earlier than he does the Sun itself. And that is a proof that the Earth goes around the Sun. You may still explain the geocentric model that way, but that turns out to be even more complicated. Oh yeah, we can explain the sidereal and solar days difference by just making the Sun and the stars move at different rates. The Sun goes around the Earth in 24 hours. All of the stars move as one on the celestial sphere in 23 hours and 56 minutes. The axis of that celestial sphere is near the polar star Polaris. There is no clear-cut evidence as of yet from this specific lecture that we just finished that the Sun is in the middle rather than the Earth is in the middle. If you see the links below, you can notice that the model where the Earth is in the middle is just as convincing. A bit contrived, mind you. We have to have the Moon going around the Earth in 24 hours and 50 minutes, the stars in 23 hours and 56 minutes. All of the stars have to move as one. When we didn't even get into the issue of what the planets are doing. But this model works, as does the heliocentric model. We will see in the next two lectures how we finally got convinced that it is the Earth that's moving and spinning rather than the Sun.